Welcome back, everybody. I just added something to the notes right up here. So this problem was where we left off, and the answer was y equals 6/5 x plus 2. Now, there is a fast way, which I've written here. I think it's like I call it the easy way because it's fast. And it's because we already see that the y-intercept is 2. But and so if that's the case, then you can immediately know what the b value is in the slope-intercept form. B is 2, so all we need to do is find the slope, because then we have y equals mx plus b, which we can do by either using the slope formula using these 2 points, or if they're nice points, we can use just the rise over the run, which in this case we did do. But you can always just use the 2 points and use the slope formula, especially useful if you don't have nice numbers. And then you have M, you have B, you have everything you need to get it. But that is only useful if you know the y-intercept right off the bat. What if the line looked like this? Is that a y-intercept of 2.5 or 2.4 or 2.45? Heck, it might even be square root of 5. You don't know. So in that case, you can't just find the b value immediately. And instead, it's better to just use point slope form. So that's the way that we're going to do it. So first find the slope, which m is equal to 12 over 10, just like before, which reduces down to 6/5, and use either point. We'll use 5 comma 8. All right, that's 5 comma 8. Yeah. So you can use either point in point slope form. It doesn't matter the point as long as it's just a point on your curve. I guarantee you, if you use the point -5 comma -4 in your answer, you'll get the same thing. It'll just be, it'll look different, but if you simplify it down into slope-intercept form, it'll be the exact same answer. So I just decided to use 5/8 so I don't have to deal with any negatives, but there's no harm in choosing this point instead. So now that we have a point, we have the slope, we can use the slope point slope form, which once again is y minus y sub 1 equals m times x minus x sub 1. That's y minus 8 equals 6/5 times x minus 5. Or if you really want to simplify it, you get y equals 6/5 x minus 6 plus 8, which becomes y equals 6/5 x plus 2. So it all depends on how you want things done. That is the quote unquote longer way because it required a little more work, but it works on everything, even if you don't have a nice y-intercept. So I prefer that method purely because then I don't have to memorize 2 different things. I just need to memorize one thing. Because if I try and memorize this method only, then I also have to memorize this method when it comes to ones that don't have a nice y-intercept. But this one works even if I do have a nice y-intercept, so I can just bypass it. Less I memorize, the more I can spend time studying the important things in life.
Is that one the same as y2 minus y1?
Over x2 minus x sub 1. That's the slope formula. So that can be used to find this.
Yeah.
Yeah. And you can use that. And honestly, it's better to do that in practice because A, you get more practice with it. B, it is more generalized. It can work with any situation. Like what if instead of these points, they didn't give me any nice points. They gave me like 7 or that's going to be 4.1 comma 6.9. Then trying to find the rise over the run is a much more challenging ordeal because exactly how much did I go up, how much did I go over, it's hard to tell. So the slope formula would definitely be a good idea. Any questions on that? Okay. Then we move on to perpendicular and parallel lines. The real important thing So let L sub 1 and L sub 2 be lines so that one of them is y equals m sub 1 plus m sub 1x plus b sub 1, and one of them is y equals m sub 2x plus b sub 3. The two lines are called parallel if they have the same slope. And we denote it with two slashed lines that are parallel, even though I didn't draw it right. Like that. So that's the symbol we utilize for parallel, for lines being parallel is two slashed lines. Hence, it kind of looks like two parallel lines. And so mathematically, what we're saying is if they have the same slope, it means that M1 and M2 are equal. So mathematically, we would write M sub 1 equals M sub 2. And the important fact about parallel lines is that they never intersect, at least in Euclidean geometry, the geometry that we all know and love, or despise, whatever your opinion is. But in Euclidean geometry, parallel lines will always increase at the same rate and they will never, ever intersect. There are other forms of geometry later on in mathematics, but that's for where parallel lines could intersect, but that's for very, very bored mathematicians. Nobody important would study that. But either way, I think that's really cool. Like we've been told that since forever that parallel lines will never intersect. But your eyes actually can change that perspective for you. If you've ever looked at like one of those images of a train track and it's going on and on forever, it looks like they're eventually meeting, right? If you look at a train track straight on as it goes perfectly straight for like 100 miles, it eventually looks like the two beams are coming together. It's kind of what's happening. But either way, parallel lines never intersect for us and for basically every math course you'll take on from here on out, unless you become a math major, which why would you do that? The other option are perpendicular lines. So two lines are perpendicular if they have opposite reciprocal slopes. Opposite reciprocal slopes. And we denote it by an upside down T. Note it by an upside down T. In later math classes, you'll stop calling it perpendicular and you'll start calling it orthogonal, which sounds way cooler, but regardless, we'll call it perpendicular up until about math 283. Because that's when we start dealing with three dimensions and perpendicularness doesn't make as much sense. Opposite reciprocal, what does that mean? It means in practice, a flipped version with the opposite sign. So as two examples, if you had positive 4/3, the opposite reciprocal would be negative 3/4. The fraction is flipped and the sign is changed. It went from positive to negative and the fraction flipped. If I had something like -2, the opposite reciprocal would be, is positive 1/2. Because remember, you can treat anything as over 1. So we flip the fraction. So any number can be written as a fraction. Just key note about that. So if your slope is -2, that's -2/1. So the opposite reciprocal would be positive 1/2. Mathematically, the way we would write that is that m sub 1, color, m sub 1 is -1 over m sub 2. A lot of textbooks will actually write that as m sub 1 times m sub 2 is equal to -1, but that's really putting the cart before the horse in mathematics. That's something that we study much later on in a course called differential geometry, talking about orthogonalness and how it has to relate to -1. It's a cool concept, but not necessary here. In practice, it's just best to know opposite reciprocal. And then the key thing is that perpendicular lines, they intersect directly at a 90-degree angle. And I believe that's probably the reason why we use this symbol, because it makes two right angles if you've drawn it perfectly. You might be saying, well, why don't we just draw it with two lines intersecting at then that looks like a plus sign. And or maybe we try and do it like this, but then it looks like a multiplication symbol, a time symbol. So I'm assuming that's why we do the upside down T, but either way. So find the equation of a line that is parallel to the function f of x equals negative 7x plus 3 and passes through the point 5 comma 6. Couple things to interpret in this problem statement. Please remember, f of x is synonymous with y. So f of x equals 7x plus 3 and negative 7x plus 3. That is a line because it can be rewritten as y equals negative 7x plus 3 because f of x and y are synonymous. They mean the exact same thing. A function value and a y value are no different. So let's now look at this problem. The problem is saying we want to find the equation of a line. Okay, there are two things that are needed. Either we need 2 points or we need the point and a slope. We are only given 1 point. So there must be a way to find the slope. And so slope of the given line is negative 7. The slope of the given line, because it's already in slope-intercept form. It's already in mx plus b format. And so the m is the slope, hence this one has a slope of negative 7. And because our line is parallel, that means our line has m sub parallel, which is equal to negative 7. So we found the slope, we have a point, we have everything we need. So just so we're clear what I'm writing here, the given line, the f of x, it has a slope of negative 7. That means that our line, which is parallel, that's why I've written m sub parallel, m sub, the symbol for parallel lines, is also equal to negative 7. And that means taking this information, so m parallel is equal to negative 7, and we have the point 5 comma 6. So you can use the point slope formula. I mean, you can solve for b as we suggested earlier on, but I really don't recommend it. I'd rather us just do slope-intercept point slope form. So I'm going to rewrite it one more time because it's never a bad idea to practice writing it since you will need to memorize this. Y minus y sub 1 is equal to m times x minus x sub 1, where x sub 1 is 5, y sub 1 is 6. So it's going to be y minus 6 is equal to negative 7 times x minus 5. Or if you really want to simplify it, oh man, pen is out of battery. You'd have to, why did I write a 0? We're writing a 0. Oh, it's really dead. All right, how we all doing?
You can do, just instead of doing the y and then the x, you can't just put, substitute the 5 in the x and just put the 6 for the y.
You could, and then solve for the b value. That's fine. It's just I find that this format is better. It's faster, in my opinion. It requires less overall algebra to do, and it later on in mathematics it tells me more. And I'll explain that in just a second. Thank you for bringing that up. So if you do that, then you get y equals negative 7x plus 35 plus 6. So you get y equals negative 7x plus 41. So you can get either format. Either one is fine. I just prefer point slope form because in future math courses in calculus, so don't draw this, but this is just something that you're going to have to do. In calculus, you're given a curve, let's say it's like that, and you want to find a line that is tangent to the curve right there. So when you find the equation of the line, the y-intercept doesn't matter really too much. All we care about is where it intersects the line, which is the point. And so with this one, I mean, it's not perfect thing, but what this would tell you is that the tangent line occurs at 5 comma 6, with a slope of -7. It would tell you exactly where you need to go. That's the reason why I like it more. It has better applications for future math courses. That being said, my age-old like my adage for this class is once again, if you need to use your line for something, put it in slope intercept form so that it's easier to work with because there's less stuff around. It's only 3 terms instead of 4 or 5 terms. But if you're just done after you find the line, keep it in slope intercept form. Apparently, it came to my attention that if you do that on Alex, it'll say it can be simplified. Yeah, it could, but it's better in this format, so I don't know why. So just don't listen to the Starbucks barista. Don't care about it. Just keep calling a large caramel macchiato. Just keep calling it that. Just introduce a little bit of frustration into the lives. It's good to be frustrated.
That's what you do with your child every day.
Yeah, you have to frustrate them every day.
I did it in the other way.
Uh-huh.
The y equals mn plus b.
Uh-huh.
I got b being -41.
Let me check it in a moment, and then we'll see what's going on. Okay, and I'll see what happened. So the next one, write the equation of a line that is perpendicular to 2x plus 7y equals 12 and passes through the point -4, 4. Now, once again, we're trying to find the equation of a line. So as soon as I read that, I want the equation of a line. That means I either need 2 points or I need the point and a slope. I'm only given 1 point on my line. It didn't tell me any other point, so there's no way to create it with the 2-point option. There must be a way to find slope. And it's from the fact that this line is perpendicular. We need this line's slope to find ours.
It always has to say perpendicular.
It could say parallel. So similar question, it would be like find an equation of a line that's parallel to that. It would still be the same process, but instead of making the slope and opposite reciprocal, we'd make it equal to it. So that's the only difference. But it could say perpendicular, it could say parallel. So in this case, that line, 2x plus 7y equals 12, that line is in general form, which is great for linear algebra, but not useful in terms of slope. So we'll write it in slope intercept form. So we get 7y is equal to -2x plus 12. So what I did here, make sure you can see it. I wanted to get the y by itself to get it in slope intercept form. So I had to subtract 2y, but I don't want 7y equals. I want y equals in order to be in slope intercept form. So I'll divide both sides by 7, which gives me the curve y, the line -2/7 x plus 12/7. And yeah, that's a nasty fraction for its y-intercept, but we don't care about that line's y-intercept. Doesn't matter to us. The only thing we care about from this line is its slope. And so the slope is -2/7, which means our slope, which is m sub perpendicular, is +7/2. Because you flip the fraction, change the sign. That's the opposite reciprocal. And so m sub perpendicular, m sub upside down t means our perpendicular slope, which is what we want. And we already have the point. So we get y minus 4 is equal to m, which is 7/2, times x plus 4, because it's x minus x sub 1. So it'll be minus -4 in the formula. And we can leave it like that, or we can simplify it and get y equals 7/2 x plus 14 plus 4, which gives us y equals 7/2 x plus 18. Either way is fine. And once again, when it comes to the exam time, if there is a question, which there probably will be, I mean, I'm not really being surprising here, right? This is one of the 7 sections that's going to be covered on this exam. There's going to be a line question. So in that case, if there is a question where I'm asking you to write the equation of a line, I will not care what format you leave it in. I will make sure that both formats, like I have both formats on my grading guide so that I can give you credit regardless. Any questions?
The only reason why you switched it is because it was perpendicular.
That's correct. If it had said parallel, I would have used -2/7, and that would have been here. But the point would have still been the same because it was the given point. Yeah, if it said parallel. Yes, I'm aware that it's basically dead. It's like 7 years old. So, any questions?
What kind of pencil is it?
That's an Apple Pencil. I got it for Christmas like 7 years ago.
You want?
Say what?
I think I got a charger if you want.
Oh no, it's fine. I'm using my I found out a long time ago, like my wife told me apparently I can charge it with my phone. So, well, I mean, I can charge it with the iPad, but apparently the iPad cannot handle Zoom at all. It kills the battery within like 30 minutes. So like this thing is at 100%. If I were to unplug it and start charging it with charging the pencil with my iPad, it would probably be at 50% by the end of the day. By the end of the lecture. So, anyways, next one. Write the equation of a line that has an x-intercept at 4, 0 and is parallel to this line here. Okay, well, it gives us a point and it doesn't give us another point, so we must be able to find the slope. But that's what since it says parallel, we already know that we're going to try and find the line of the slope of this line. So, need this line slope for ours. And this line slope, I'm going to use the slope formula. Purely, I mean, like, because they gave us nice points. They gave us -4, -6. So it's already on a nice grid line, and same thing with the top point. So we could use rise over run, but let's just get practice with the slope formula because it doesn't hurt to do so. So here is the point, -4, -6, and here's the point, 1, 3. It doesn't matter which one I make my x sub 1, y sub 1, and which one I make my x sub 2, y sub 2. So I'm going to make this one my x sub 1, y sub 1, and this my x sub 2, y sub 2. So m would be y sub 2 minus y sub 1 over x sub 2 minus x sub 1, which would be 3 minus -6, so 3 plus 6 over 1 minus -4, so 1 plus 4, and that's equal to 9/5, and that doesn't reduce anymore. But I guarantee you, if you did the rise over the run, you would get 9 over 5. You'd have a rise of 9 over a run of 5. I just like using the slope formula because it's more applicable to any situation, which, I mean, real life is never this neat, right? If you were trying, like, if this was trying to model some type of cost function or something like that, or a data plan or something like that, it would not be nice numbers like this. It would be decimal points and nasty stuff. So it's best to use the slope formula. So with that in mind, that means that our slope, which is m sub parallel, because it's a parallel line, is also 9/5. So we have our slope. We have a given point on our line, 4, 0. So we have everything we need to write the equation of our line. Y minus y sub 1, so y minus 0. Don't get it twisted with the x sub 1, y sub 1 that we labeled already. So that's the problem with an abusive notation. This is our new 4, 0 is our new x sub 1, y sub 1, because we're talking about our line, not the given line. So don't get that twisted. So y minus Y sub 1 equals m, which is 9/5 times x minus x sub 1, which is 4. Or, luckily for us, there's no needing to move anything over because we're just subtracting 0. So you get y equals 9/5 x minus 36/5. Either way is fine. There you go. Any questions on that?
Yeah, where'd you get the 4-0 from?
That was given in the problem. It says it has an x-intercept at 4, 0. No problem. Sometimes we get so focused in on what we're doing that we forget some information from the beginning.
But would you use is it the same thing no matter which one you use? Like if it was like a more difficult problem, would I have to simplify it even more? Or would I use the first one?
You use these ones. Either one of these would be fine. You don't need there's no need to simplify it any more than this.
So when you're finding this equation, use the old way, and then once you got the old way, then use the new way to solve further. Okay.
So, and with regards to Ben's question, I think this is a very, very good segue into the next section of this notes, the last section of this notes, which is the applications lines. Everyone's favorite thing in the world, word problems. It's all of our favorite stuff. It's what we lived for when we were taking math courses, I know. Right? So the key thing is to remember that the slope is a rate. That's the first key, and the second key is to define your variables. The slope is a rate. So if you ever see something as blank per blank, or it says feet over seconds or something like that, if it's a rate, that means that that's going to be the slope almost always. Unless it's there might be a few cases where that wouldn't be true, but for the most part, as soon as you see a rate, that's going to be the slope. And then the other thing is to define your variables. If you do not define your variables, you're not doing a good job at presenting your mathematical argument. That being said, if you finish off without and you mention the units there, that's fine. I'll give an example on the next one. So let's go through this first one first, and then we'll talk about what I mean by defining variables. The monthly cost in dollars of a phone plan is a linear function of the total call time. This is before your guys' time. This is my generation's aspect of phones. This is a moot point nowadays, but it used to. Does anybody remember being charged by the text message?
We used to have to call on Fridays after 8 p.m. because it was free.
Yes. If I say 10, 10, 220, does anybody know what I'm talking about? One person. Okay. I'm not that old yet. 10, 10, 220 was for collect calls. Oh man. That's an old time joke. But anyways, so the plan starts at $34 and you're charged 11 cents per minute. So the 11 cents per minute of usage is the key here. This tells us that the slope is 0.11. And it also tells us what the variables should be. Now, you can use whatever variables you want. The convention is to use X and Y, but there's nothing stopping us from using P and Q or A and B. It's just X and Y are usually, we already kind of have an established routine about them where X is the independent variable and Y depends upon X. So in this case, it seems like the independent thing is the amount of time that you use, because the amount of time is independent of the more specifically, the cost of the plan changes with how much time you use. So we're going to let X equal time. in minutes and y equal money. It does not need to be some super long, drawn out thing where you write it in like full English. As long as you have like a way to understand what X and Y represent, that's fine. So I mentioned that I wanted to get to Ben's point, but I forgot to say what the point was. It's with word problems, the key thing to do, it's counterintuitive than the way we usually solve exams, but you need to take it slow. You need to take word problems slow. Digest all the information that's present because everything in there is deliberate. I mean, like, there might be some situations where like information is not necessary, but I try to make sure that only the important stuff is mentioned in a word problem. So everything that's in there is important. The plan starts at $34, meaning that if you don't call anybody, you will still be charged $34 for that plan. So if t is 0, or if x is 0, then the plan costs $34. If x is 0, y is 34. So the y-intercept is 34. Remember, the y-intercept is where you cross the where you cross the y-axis. And that happens precisely if your x variable is 0. So that gives you your b value. So we actually have everything we need. This is b. So we have that the equation should be y equals 0.11x plus 34. And one thing you should do is make sure that everything works out. X is measured in minutes. So this, you don't need to write this down, but we want to make sure that at the end of the day, y does give us money. So it's $0.11 per minute. And if I multiply that by, let's say, 33 minutes, you'd notice that the minutes would cancel and we'd only have dollars. And we'd be able to add those dollars to the dollars that are already present, the $34. So our answer will make sense. If it had been 0.11 minutes per dollar, this formula would not have worked because then the minutes wouldn't be able to cancel. So we've got the right setup. And then we have to ask ourselves, how much would be charged if you were on the phone for 4 hours and 22 minutes this month? So it is not going to be 4.22 because first and foremost, our time is measured in minutes. So we need to convert the 4 hours and 22 minutes to 4 hours and 22 minutes to purely minutes. So let's read this last statement. How much will your phone bill be? We want y when x equals 60 times 4 plus 22. And by the way, there is a way to solve this problem without a mathematical formula. You can skip the mathematical modeling if you so choose with this problem, but that's not always the case. So it's good to get practice working with these things, even if you could solve this without math, without algebra.
So B would always be the fixed number.
Say what?
B would always be the fixed number.
Yes, it's going to be a fixed like starting value. If it says initial or if it says starts, that's going to be talking about a y-intercept. And so 60 times 4, that's 240, plus 22, that's 262. So we have y of 262. So I'm writing this in function notation, by the way. Y of 262. That's not, because you could also think of a function as y of x. Is equal to 0.11 times 262 plus 34, which is equal to 62.82. So in my class, John Doe student boxes this answer in and gets full credit. In another person's class, maybe a more vindictive teacher, they get marked down. Why? Because they didn't put the dollar sign. However, I would argue that by mentioning at the very beginning that y is measured in dollars, that the dollar sign is clear from the context. So that's what I'm saying when it comes to defining your variables. If you don't define your variables, if you omit this step, then you do have to write the dollar sign. But if you do include it, you don't need to. It doesn't hurt to draw it, to write it down. But that being said, if you define your variables in another class after this course, and your teacher marks you down on writing the final answer, even though you define what the variables were, please let me know, and I will come to your aid. I will go fight them on the battlefield, just bust out my sting sword.
You actually do that.
Yeah, I still got my sting sword from Lord of the Rings. My other class, was it this class that was asking about Lord of the Rings, or was it the other class? Okay. Who has watched Lord of the Rings? Okay, you all need to watch it. It's a cinematic masterpiece. It's one of the most iconic pieces of cinema that's existed. You gotta watch it. The extended edition. The extended edition, seriously.
Have you seen the old one, the cartoon?
Yes, I love the cartoon one. Well, I watched the Hobbit one. The Hobbit one was excellent. I haven't really. It's been a long time since I've watched the cartoon Lord of the Rings, but the Hobbit was excellent too. But either way, I'm getting sidetracked. Point being is, please argue with your teacher. If you've defined your variables and they mark you down, even though you didn't include it in the final answer, you should tell them it's already stated. I already stated what y was measured in. So, haha. All right. Any questions on that one? Yes.
The formula, are we using your preferred one or are we using the mx plus b?
So in this one, it just so happened that everything fell into place with the slope-intercept formula because it already gave us b and it already gave us the slope. The next one is one where I would say that it would be important to use point slope form. So suppose you are incredibly bored and you are watching a candle burn. And you'll notice that the height is a linear function of the time it's been burning. After 2 hours of burning, you were really bored, so you decided to watch it, and the candle has a height of 23.6 centimeters. And after 5 hours, the height of the candle is 12.9 centimeters. What is the initial height of the candle? The fact that it said it's a linear function means that we're dealing with lines. So, and we see that the height depends upon the time. So we'll let x equal time, the independent variable. And you can even get by with just saying time or hours. You don't have to say time, parentheses, hours. You can do whatever you want, but as long as it's clear to you what you know you're talking about. My requirement there is purely to remind you, in my class, you need to show enough work on your exams so that a fellow classmate would be able to understand it by looking at the work. If you don't define your variables, they probably would ask, what does X and Y represent? Ben.
Okay, if we were doing this on our own, could we make y hours instead?
You could, but it will look different. And how you solve it will be slightly different. It's possible, but maybe we can try that if we have time. But like if you make the wrong thing, it's never too late to just restart. If it's starting to look way too complicated and like not fitting into the right formula, then I would say just go back to the drawing board and try the other way. And so y will be height. In centimeters. Though you could just write y equals cm and that would be fine. Okay. Unlike before, we're not given a rate. So we don't know what the slope is off the top, like immediately. However, we're given a lot of information that we just need to make sure we understand what it's doing. After 2 hours of burning, the candle has a height of 23.6. So from the red, x equals 2 implies y equals 23.6. Or more specifically, we have the point 2 comma 23.6. After 5 hours, we have the exact same thing. From the blue, we have the point 5 comma 12.9. By a similar argument, we're saying that when you've been watching it like after 5 hours, so when the x value, which is measured in time, when the x value is 5, the y value is 12.9. That gives me an ordered point. And I can use these 2 points to find the slope. M is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So I'm going to make this my x sub 1, y sub 1, and this my x sub 2, y sub 2, though it doesn't matter which one's which, as long as you're consistent. So y sub 2 is 23.6 minus y sub 1, which is 12.9, divided by x sub 2, which is 2, minus x sub 1, which is 5, which is approximately negative 3.57. I believe it's negative 3.566 repeating, but we'll round that to negative 3.57. On an exam, my usual recommendation is to round to 2 decimal places. That usually is sufficient on most things, but for early rounding, it's probably better to round to like 3 to 5 decimal places. By the way, I realized that one thing I didn't mention is why we're doing this. So whenever we're doing a word problem, we should always ask ourselves, what am I trying to find? I want to find the initial height of the candle. I want to know why the y value when the x value is 0. I want the y-intercept, truly, but we can still just do it by plugging in y equals 0. Sorry, x equals 0. What's up?
Because you're graphing, right?
Yep.
You can imagine it as graph.
Yeah, it's a decreasing line.
Yeah.
Yes, exactly right. And so the reason why we're doing all of this is in order to know where the initial height would be, we need to know how to model that function. Because if we find the model of that function, we can then assume what the values would be at any given time. So we have the slope, which is negative 3.57. What this is telling us, because y is measured in centimeters and x is measured in hours, it's saying that it's decreasing by 3.57 centimeters per hour. That's what this formula is saying. So we can even add that if we want to. It's centimeters per hour because y is measured in centimeters, x is measured in hours, centimeters per hour. Now we can use either point. So, and we'll take the point, we'll use this point here to get y minus y sub 1, so y minus 12.9 is equal to negative 3.57 times x minus 5. And then we need to use our calculator because I don't want to deal with decimals in my head. That seems like an unnecessary use of brain power. So I'll bring out the old calculator and say, so negative 3.57 times negative 5 is 17.85. So we have y equals negative 3.57x plus 17.85 plus 12.9. So y is equal to negative 3.57x plus 30.75. Notice this problem is asking me to use my equation. That's why I've written it in slope-intercept form. If it asked me to just find a linear model for my the height of the line, I would probably just stop right here. But I'm going to be using it to find the initial height. Any questions on that? Yes, Alita.
Use minus 12.9 on the other side of like,
I'm using this point slope form.
well, yeah, I got the formula, but why is it 12.9 specifically?
Because I had already labeled this point X sub 1, Y sub 1, but there'll be no problem using this. In fact, in my notes when I originally did it, I used the second point, but I get the exact same line. So,
So, one,
exactly right. So, it wants the initial height. We want y of 0. So, y of 0 would be negative 3.57 times 0 plus 30.75, which is equal to 30.75 centimeters. Though I don't need to include the centimeters because I already established what y was measured in from the very beginning. But if you didn't include that, that would be fine as long as you finish off with writing what the dimension is. Then it will be eventually clear from the context what x and y mean. Yes, Connor.
So if I could just see like that, we're gonna double the -3.57 to like whatever 7 would be, I think that would be like -7.
Mhm.
And then could I just add that into the original height, because I used the 2 hours of burning to multiply that, so it'd be double the time, and then just add it into the height and make it the same number, without having to do all the algebra at the bottom.
So you're saying like trying to find the rate and then go backwards twice from
Yeah,
that?
like when you wrote that down, I already got the answer, because it was, I just used the 2 hours, then multiplied by 2, and I got 30.
Yeah, if you don't want to be fun.
But I was just saying, like, or is it gonna be like visible, or do you have to write all them?
If it does not require work, like if you can do it with logic, that's fine. That's still mathematically valid. Unless I'm asking you to create a linear model, in which case then you have to write it. But no, if you want to logic your way through it, you can rain on my parade. Fine.
I just don't like doing math. I'm sorry to tell you that.
Hurts my feelings. I'm kidding. Like that's totally legitimate. That's a completely legitimate way to do it. Okay. Any other questions? All right. Now those are the boring applications. Let's look at the fun applications, which are math applications of slope and lines. So the average rate of change. Let f be a function defined on an interval a to b. Then the average rate of change of the function f on the interval a to b is given by the formula m sub avg equals f of b minus f of a over b minus a. So some people will call that, some textbooks will call that m sub sec for what we call the secant line. And that has close relations to calculus with the tangent line. And once you take Math 127, you'll see that there is a small connection between secant and tangent. So there is a reason to call it the secant line, but it's better to think of it as an average rate of change. It is trying to find like you do this without even realizing it sometimes. So if you're trying to figure out your average speed on a road trip, right, there's going to be some areas, especially if you're in Texas, where the laws don't apply. You can go 85 miles per hour, no one cares. Seriously, like there's some places where like Texas is crazy. Don't go there. It's crazy what the people drive. Yeah,
Why they drive that fast is because it's so flat and long.
it's such a huge state. It's too big. It's way too big. Say what?
There's no one on the road.
Not really, no. But anyways, if you're like some places you're going to be driving 90 miles per hour, sometimes you're going to be driving in construction zones where it's like 30 miles per hour. And if you want to find your average rate of change, your average speed, you take the total distance traveled and divide it by the total time that it's taken. And that gives you your average speed. So average rate of change is not something new. We just have a formula for it. And you might be thinking, Phil, do I really have to memorize another formula? No, you don't. That's not a new formula. This is just the slope formula with function notation. That's all it is. It's just doing it, and I'll prove it to you. Because we need to understand our concept of functions. It's very, very important. So we've got an interval A to B. So let's label these points right here. This is A, and this is B. Then the y value of this point that has an x value of A is the function value there. So this value is f of A. And the further value over here, that's f of B. So in particular, this first point, this is the point A comma f of A, and this is the point B comma f of B. What if I made A comma f of A my x sub 1, y sub 1, and B comma f of B my x sub 2, y sub 2? I'd be finding the slope of this line, and that would just be this. So it's not a new formula. I will provide the average rate of change formula on the exam, but I really don't need to. It's just the slope formula, just written with functions instead of with y's and x's. Is that any questions on that? We call this line right here the secant line, and the average rate of change is the slope of that line. So that's all this is. So like in this case, this is your x sub 1, y sub 1. And this is your x sub 2, y sub 2. That's all it is.
You ask that third point,
What third point?
like later on down the road?
This one over here.
Yeah.
Well, so it's only on a specific 2-point interval. So that is another point on it, but this actually leads to what tangent lines are all about. Tangent lines are all about local, like where it hits very, very close to where those 2 points are. So yes, it will this secant line. This secant line will extend, but we're really only interested in it here. So we don't need to worry about where it is outside of that area. So find the average rate of change of the function on the interval 1 to 3. It's telling us by saying the interval 1 to 3, this is saying that A is equal to 1 and B is equal to 3. So M sub AVG, there's a reason why we use M, by the way. It's because it's a slope. And so it's just the slope formula. We just use function notation. So it would be f of 3 minus f of 1 divided by 3 minus 1. And I'm going to compute f of 3 and f of 1 off on the side. F of 3 would be plugging in 3 for every instance of x. That's how function notation works. So it would be 3 cubed minus 3 plus 2, which ends up being 27 minus 1, so 26. And then f of 1 would equal 2. I'm writing it on our notes so that we see what we did. We plugged 3 into the function. But later, like if you're doing this on exam, you could just write f of 3 equals 26 and f of 1 is equal to 2. Hell, you could even just plug it in immediately into the problem, and I give you full credit. It's just so when we're taking notes, we see what we did back in the day when we're reviewing this for the exam. So this will become 26, that's f of 3, minus 2, which is f of 1, over 2, because 3 minus 1 is 2, and that ends up being 12. So this is a purely mathematical object. But you could imagine maybe the trajectory of your road trip is modeled by that curve, x cubed minus x plus 2, on the interval from 1 hour to 3 hours. And then you could find that would tell you that your average speed was 12 miles per hour in that time period. You were in LA traffic. Boom, roasted. Do not like LA. Too busy. But either way, there is reason to study this for average rates of change, like in a real life context. But I don't really care about real life. I'd rather spend time in the virtual and mathematical world, right? That's the more fun stuff.
But you like working with real numbers.
Yes. So it's a love-hate relationship. Noel, did you have questions with stretching? The next one. It says y equals x plus 2 from a equals 7 to b equals 10. It's another way to say the exact same thing. The only difference is instead of having a function, we have y equals, but that's just a function. Y is synonymous with f of x. So we already have a, we already have b. So it's going to be that m sub avg is equal to f of b, so f of 10 minus f of 7 divided by 10 minus 7 divided by b minus a. And so f of 10, I'm going to plug it in right away. I'm not going to compute it on the side. It's not wrong to do so, but I can do it right from the start here. That'll be the square root of 10 plus 2 minus the square root of 7 plus 2, all divided by 10 minus 7, that's 3. So that's going to be the square root of 12 minus 3 over 3, which is approximately 0.1547, depending on whether or not the question wants me to round it or leave it in exact form. Because 7 plus 2, that's 9, so the square root of 9 is 3. 10 plus 2, that's 12, and the square root of 12 is not a perfect square, so we have to leave it as is. I mean, you could write it as 2 square root 3 if you really wanted to like reduce the radical, but that's unnecessary. Ariel, yes.
The previous operation that you did, why is the order of the formula of x multiplied by 3 minus f multiplied by 1 in that order and not like vice versa?
So, a couple things. So just so we're clear, it's not f times 3, it's f of 3.
Oh,
It's I know what you're saying, but I want to make sure it's clear. It's not multiplication.
Yeah.
And it's because it doesn't actually matter at the end of the day. As long as you are consistent, if your a is first, then the a should be first on the bottom as well. So the average rate of change formula could be f of a minus f of b over a minus b, but then it wouldn't make as much sense in terms of real life because we're measuring things usually in time, and so time should go linearly forward. So you want to use your later time minus your earlier time.
so I would just focus on the result being positive then, pretty much.
Yeah. So it should be, the b value should be larger,
Okay.
but it's not required as long as you're consistent.
Thank you.
Yes. Any other questions? Last one, my favorite problem on the average rate of change, once it loads, is the graph of a function g is given below. Find the average rate of change from x equals -4 to x equals 2. Another way to say the exact same thing. It's asking for the average rate of change, but instead of giving you the a and b values, or giving you the interval, it's talking about the interval by saying from x equals -4 to x equals 2. So here, a is equal to -4 and b is equal to 2. It's saying the exact same thing, just with different words. So, oh no, Phil, I don't have the equation. That's not necessary. We have the function. That's half the battle. M sub avg would be equal to, this time we don't have f, we have g. So instead of writing f of b minus f of a, we'll write f of g of b minus g of a. So it's going to be g of 2 minus g of -4 divided by 2 minus -4. Okay, that's by definition. But we don't have the equation of g, so we have to find g of 2 a different way. We have the graph, And g of 2 is the function value. It's the y value when x is 2. So let's color code it. Let's use green for g of 2, and let's use purple for g of 4, g of negative 4. G of 2 would be right here. G of 2 is 7 because it's the y value on the point where x is equal to 2. And g of negative 4 is the y value when x is equal to negative 4 on your curve, and that would be right down here. So g of negative 4 is equal to negative 5. So we have 7 minus negative 5 divided by 6, which ends up being 2. Don't draw this pink line. I'm just drawing something for observational purposes. Notice that the slope of that line is 2. If you zoom in really quick, a rise of 2 over a run of 1, rise of 2 over 1, rise of 2 over 1. It's got a slope of 2. It's the slope of that line. That's what the average rate of change is. Hector, do you have a question? Okay. So that is the end of lines. Does anybody have any questions on that?
How'd you get the 7?
That's g of 2, which is the y value at 2, which is 7 here. Similarly for g of negative 4. All right, let's take our first break. Let's come back at 10:42, and then we'll start up 1.6. People watching the recording do some push-ups. All right, and we're back, and we're starting up the next unit, which is 1.6 on the transformations of functions. So in order to talk about transformations of functions, we need to know what I like to call the parent functions. Now, the book will go over only a few of them, whereas I think it's better to know the general form of all of them. So f of x equals b, where b is constant. So that is a horizontal line. So let's just make this value b right here, and then a horizontal line through that. If you have f of x equals b, that's a horizontal line. And the domain of that function is all real numbers. The range is just the value b. So instead of being an interval, it's a little curly brace with a b in it. This is the only function that has a singleton value as its range. The only parent function. And then you'll see that I said important points. Now that'll play a role in just a moment when we talk about transformations, but we'll get there. The important points, I usually pick 3, and that would be negative 1 comma b, 0 comma b, and 1 comma b. Now we didn't talk about even and odd functions, but this is an even function. It's symmetric with respect to the y-axis. If you were to fold the paper hot dog style, right? Because yeah, if you're to fold it hot dog style, it would be exactly the same on both sides. Then you have the identity function, the most important, like the original function in all its glory, f of x equals x. And that is a line with slope 1. So it just goes from the bottom to the middle like that. And that is y equals x. Its domain is all real numbers. So negative infinity to positive infinity. And its range is all real numbers. Its important points are negative 1 comma negative 1, 0 comma 0, and 1 comma 1. And this is an odd function, which means that it's symmetric with respect to the origin. So if you have a point on one side of the origin, then the opposite side will have another point. So for example, here's 1, 1. Here's negative 1 comma negative 1. Here's 2, 2. Here's negative 2 comma negative 2. It's an odd function. We don't really need to worry about even or odd, but just so you have it. And then we have the absolute value function, which looks like a V. I should plot those points actually. So there's 0, 0, or 0, 0, -1, 1, and 1, 1. This one has the point 0, 0, 1, 1, and -1, comma 1. Looks like that. And you'll notice that the left half of the graph is just a flipped version of the x value of the x function. If I took this piece and I flipped it upwards, it would give me the absolute value function. Just a fun little observation. And it's just because the absolute value, what it does is it takes all the negative numbers and flips them over. So the domain of this function is -infinity to +infinity. Its range is bracket 0 to +infinity because it takes in only positive, it spits out only positive numbers, yes?
This might be a silly question, but why does a flip happen on the 0 and not before or after? If that makes any sense.
Yes, it happens because before 0, to the left of 0, all the values would be negative. So the absolute value function, it makes all those things positive. No, it's a very, very cool question. As a fun little tidbit, just if this is your function here, if that's f of x, then the absolute value function is this. This is the absolute value of f of x. All it does is it takes the negative portions and flips them across the x-axis.
Thank you.
Very, very fun thing. And the important points on the absolute value function are -1, 1, 0, 0, and 1, 1. Once again, I know this seems a little bit weird, these important points. They will make sense once we get to the next point, next part. Then, the textbook will only tell you about x squared, but I disagree with that. Because, in fact, oh, Darren, yes. So the range is all the y values that get attained. And because there is a point at 0, 0, so we have a y value of 0, 0 is included, but nothing below 0. So the range, you look for there's no -3 is not part of the range because there's no point that on the curve that has a y value of -3. Same thing with -2, same thing with -1, same thing with -0.5, but 0 is in the range because there's this point that has a y value of 0. 1 is in the range because there's this point. There's also this point, but that has a y value of 1, and so on and so forth. Is that okay?
Look, this a little bit doesn't make sense for children because 2 has a point on 0, it doesn't have bracket.
For number 2, well, it goes from -infinity to +infinity. So all the points are in the, all the y values are in the range. So the textbook will only say x squared, but it's actually true in general for any even number. So f of x equals x to the n, where n is even. So for n even. So I'm talking about things like y equals x squared, or x to the 4th, or x to the 200th. Any of the even powers of x. Any of the even powers of x. They always have these 3 points. They have -1, 1, 0, 0, and 1, 1, and they look like a U shape. They're Soulja Boy's favorite function.
That's what that was.
That was... No, Soulja Boy's still relevant, right? Crank that Soulja Boy, right? We still do that? What?
Never got though.
Exactly. That's see, Eric knows what's up. Thomas apparently doesn't. He doesn't know about Soulja Boy.
You pulled Soulja Boy out of nowhere.
It's you. It's a U shape.
Oh, because it's a failed concept.
No, because the song, it goes, you. Okay. I feel like I didn't need to explain that much, but now I have. Okay. So x squared in particular looks like that. The higher the degree, the higher the power on the exponent, the more steep the graph looks. So that's what x squared looks like. X to the fourth will look kind of like this. And then if you get to like x to the 200th, it'll almost look like this. So they always form this U shape. It's just when you go into higher degree powers, it looks more and more jagged. If you're talking about x to the 2000th, it'll almost look like this. It will look like it's two vertical lines, but it's not actually. It's just it grows very fast because 1.1 to the 200th, let's just 1.1 to the 200th is 189 million. So at 1.1, x to the 200th is already at what is at 189 million. So that's the difference there. But the point is that every single even power of x always has that U shape. So the domain, by looking at this, the domain is all real numbers. The range is bracket 0 to positive infinity as well. And those three important points are -1, 1, 0, 0, and 1, 1. And then you have the odds. If you have f of x equals n to the odd, the textbook will only to cover y equals x cubed, but it works in general. If you have, so for m odd, so we're thinking of things like y equals x cubed, x to the 7th, x to the 201th, and so on and so forth. Any odd power of x will have these 3 points. It'll have -1, -1, 0, 0, and 1, 1. And it'll look like this cool squiggle. Like that. Roughly. Doesn't need to be perfect. I'm going to zoom in so you can see it better.
Is that 2 or 1?
It's -1, like so. Like you'll see that there are little tick marks every 2 tick marks. So it has -1, 1, 0, 0, and 1, 1. And much like with the even functions, the odd powers, it just gets more jagged and more steep the higher the degree. So that's what x cubed looks like. X to the 17th might look like this. So you see how it's still increasing. It's still it's not exactly a vertical line, but it just grows much faster. And then x to the 201th, that'll probably look like this.
Much the higher the exponent, the more vertical it looks.
Yes, it still has the same overall shape. It's just far more jagged. And that's because, like, I mean, we can talk about that more in detail later on, but it has to do with the bigger powers. They just make numbers get so much larger, so much quicker. And so the domain of this function, despite the way it looks, the domain is all real numbers. And the range is all real numbers. And the important points are -1, -1, 0, 0, and 1, 1. So the textbook will only cover x squared and x cubed, but I don't think that's helpful. It works for any odd power. They always look like that. They always have this cool squiggle shape. You can add more points too. Sometimes Alex wants more. I realize I should add for y equals x squared, you also have 2, 4 and -2, +4. And for y equals x cubed, you also have the points 2, 8 and -2, -8. If they want to, sometimes on Alex, they want 5 points instead of 3, which I disagree with. I think you should be fine with 3. That being said, I think it's because the Alex program needs those in order to graph it. in order for the program to actually be able to graph the best fit line, it has to have 5 points. That's my best guess as to why they want them. On an exam, all you need is 3. So those are the points for those ones. If you're dealing with x squared or x cubed, those ones become much different if it's a larger power, right? If it's x equals y equals x to the 4th, then you have 2 comma 2, 4, 8, 6. You have 2 comma 16 and negative 2 comma 16. So the ALEKS will only really work with x squared and x cubed, but it still works in general. Then we go on to the even roots. If you have f of x equals the nth root of x, where for n even, so we're thinking y equals the square root of x, or the 10th root of x, or maybe even the 200th root of x. These always have the points 0, 0, and 1, 1. And they look like this, roughly speaking. Do you have a question, Bruce?
The last point.
Oh, right here. -2 and -8. Very, very hard to see. Thank you for asking. So they always look like that. The higher the degree, the more steep it is. The higher the root. So, for example, if you're talking about the 10th root, it'll probably look like this. Still roughly the same shape, just more jagged. But it always kind of has that overarching curve to the left. And so its domain is all positive numbers, so or non-negative numbers, so bracket 0 to positive infinity. And its range is also 0 to positive infinity. It just takes a really long time for it to get to positive infinity. Right? You have to be at 100 to get to a y value of 10. You have to be at x equals 10,000 to be at y equals 100. So it takes a long time, but it does eventually get to positive infinity in the range. And so the important points are 0, 0, and 1, 1. But if you're also dealing for y equals the square root of x, you also have the points 2 comma 4 comma 2 and 9 comma 3. And I guess you technically also have 16 comma 4 and so forth, but that should be enough. Then you have the odd degree radicals. For m odd, so thinking things like y equals the cubed root of x, or the 7th root of x, or maybe even the 99th root of x. Those ones always have the point -1 comma -1, 0 comma 0, and 1 comma 1. And they look like kind of a flipped version of x cubed. With the only difference in the radical, in the root, the number of the root just makes it more jagged. The higher the root, the more jagged it looks. So if you're talking about like the 99th root, that'll probably look more like this. Still the same shape, but just more jagged. The domain of these functions is all real numbers. The range of this function is all real numbers, though it does take a while for it to get to negative infinity and positive infinity, but either way. And then the important points are -1 comma -1, 0 comma 0, 1 comma 1. And then if you're dealing with the cubed root, especially for y equals the cubed root, you also have 8 comma 2 and -8 comma -2. And so once again, the ALEKS program will really only work with like our textbook, and ALEKS will only really work with the square root and cube root. But there's no harm in knowing that it actually works for any odd root or any even root. It looks like that for all those things. And that'll actually help us down the road. That'll help us a lot when it comes to polynomials. Understanding those first two. F of x equals 1 over x to the n for n even. So we're thinking things like y equals 1 over x squared, 1 over x to the 6th, or maybe 1 over x to the 100th. Those curves, we haven't talked about them yet. We'll talk about them soon, but we have a vertical asymptote through the y-axis, and we have a horizontal asymptote through the x-axis. We'll talk more about those later. Don't worry about them for now. And these curves look, they have the point -1, 1 and 1, 1. And they look like this. They have the point -1, 1, and 1, 1. And they look roughly like that. The only difference, once again, is that the higher the degree, the more steep and jagged it looks. That is the thing I want you to understand is that the higher the degree on any of these shapes, just the more jagged and steep it looks. The domain is -infinity to 0, union 0 to positive infinity. Its range is parentheses 0 to positive infinity. And its important points were -1, 1 and 1, 1. You have more, but that's enough. We won't see too much of the last two here, but the cube root, the square root, the x squared, and x cubed, those will definitely show up a lot. Then the last one, as you would imagine, it's going to be for m odd. for mod. And now I want mod pizza.
What's mod pizza?
Oh, that's right. They don't have it here. It's a Washington thing. It's fun.
Yeah, over here we're a civilized society, so.
Washington's a civilized society.
Especially it's like Britain.
Yeah, I like the evergreen state.
Forgot that you guys have a gum.
It's a great gum wall. It's fun.
It's interesting.
1 over x cubed and 1 over x to the 97th. Well, like any odd power. They always have the point. They also have vertical asymptote at through the y-axis and a horizontal asymptote through the x-axis like that. And they have the point -1, 1 and 1, 1. -1, -1 and 1, 1. And so they look very similar, but slightly different. Instead of it being up above, it's down below like that. And then on the other side, it's like that. In particular, that's the graph for 1 over x, and then the other one's 1 over x squared. As we said, the higher the degree, the more steep it looks. So if you're talking about x to the 97th, it'll look more like this. But either way, the domain is -infinity to 0, union 0 to positive infinity, and that's actually the range as well, from -infinity to 0, union 0 to positive infinity. And the important points are -1, -1, and 1, 1. Whew. That is the library of functions. Those are all the primitive functions that we can deal with, at least at this juncture. In Unit 3, we'll talk about logarithms and exponentials, which will add on to our parent functions. But this kind of encompasses most functions that you'll encounter in your mathematical career. There are very few other ones that base themselves on anything else besides this. There's like, I mean, later on, there's what we call the step function. In Math 283, you might study the step function, which looks like I'm gonna erase this for just a second. I'm gonna take this out. There's a step function which looks like this. It's denoted y equals, I mean, there's two different step functions. That's how it's written, and it looks like this. Because it steps, it makes steps. It's a fun function. It's useful in a couple of instances, but not important in the long run. Not something that we're going to deal with. But there are other ones later on. Okay. Anyways, those are the important functions, and those important points do play a role, as we'll see once we start talking about them. So, linear transformation. Some people call this transformations of functions. Some people will call it linear transformations. They might call it something else, but at the end of the day, what we're doing is we're applying linear rules. So linear mean, like, think about what a line is. It's y equals mx plus b. You're multiplying the x value by a number, or you're adding a number or subtracting a number to the x at on the outside. Those are what we call linear transformations. So to follow along, we'll be examining this arbitrary function that I've created with an arbitrary point x sub 0, y sub 0. Sometimes we call and so I'll slip up and I'll say x naught and y naught. So that's a physics thing. They always call x sub 0 x naught and y sub 0 y naught. And the argument for why they did that is that someone said, we'll call that x naught and y naught. And they said, why would you do that? And he said, why not? All right. So x naught or y naught is what we'll say, or x sub 0, y sub 0. So the first type of linear transformation we'll deal with are vertical shifts. Let k be some positive constant. Could be 5, could be 2, could be square root 7. Who knows? Then the new function y equals f of x plus k is a vertical shift up by k units. And so we're looking what's going to happen to this point x naught, y naught. What's going to happen is your original point is going to get shifted up. That means that it's not moving left or right, so its x coordinate is going to stay the same. It's going to get shifted to x naught, comma, y naught plus k. And that makes sense if you think about the function notation. When I plug in x naught into this, I'll get the y naught value, and then I'm adding on an additional k to that. Then if you have f of x minus k, so if you have a new function that you've transformed, if you have y equals f of x minus k, that is a vertical shift down by k units. Because you're taking the function values, the f of x, and you're going to be subtracting k from the function values, the y values. So instead of it being x naught, y naught, the new function will have the point x naught, comma, y naught minus k. And so I've got kind of a visualization of this thing. Imagine like taking like on Word, you just shifting your you highlight a little image and you're just shifting it up or down. So notice that nothing has happened to the x coordinates of these. The only thing that's changed is the y coordinates have either gotten shifted up in red or they got shifted down in blue. So this y value right here is y naught plus k. And then this one down here, that's y naught minus k. That's what a vertical shift is. It's shifting it up or down. It's not moving it left or right at all. And you'll notice, and we'll be able to talk about this again in a little bit, but notice that the k is on the outside of the function. It's f of the quantity x, then plus k. The k is on the outside. That'll be a helpful tip later on, as we'll see, because we're gonna get a few of these concepts. So say what?
Yo plus K.
Yo plus k. Yo. No, why not? But you could call it yo. So, as an example of a shift up, let's talk about y equals x squared plus 2. And the shift down, let's do y equals x squared minus 1. So the parent function we're going to draw in black. The shift up we're going to draw in red. And then the shift down we're going to draw in blue. So I color coded them. You don't have to put a box around it. You could like write it in the different colors just so we see which one's which. So the parent function is x squared. That's the U shape. It's an even power of x. So it makes the U shape. It has the points 0, 0, 1, 1, and negative 1, 1. And it looks roughly like this. That is, oh, I should have made that in black. I'm sorry. I'm sorry. No. That's the original parent function. Every x to the second power or x to an even power always makes a U shape and always has the points negative 1, 1, 0, 0, and 1, 1. So shift up, it's x squared, the original function, right? This x squared, that is f of x. And then what we're doing is we're taking f of x and we're adding 2. This is a shift up 2. And this is a shift down 1. Mm-hmm. I have made each tick mark a half. So this is 1 tick mark. So the shift up by 2, all that's going to do is that's going to take each point and make its y coordinate go up 2 points. So looking at this point right here, it's going to go 2 units up to 1, 3. 0, 0 is going to get shifted up 2 units to 0, 2. And 1, 1 is going to get shifted up 2 units, 1, 2, to 1, 3. And it looks roughly like that. Same shape, just shifted up. And then x squared minus 1, that has the same kind of deal, except now we're shifting down. So all the x coordinates stay the same, but the y coordinates get decreased by 1. So instead of being at negative 1, 1, we're going to shift down to negative 1, 0. Instead of 0, 0, we're going to get shifted down to 0, negative 1. Instead of 1, 1, we're going to get shifted down 1 unit to 1, 0. And then we'll graph the exact same shape. It doesn't need to be perfect. So just to show what happened algebraically instead of or graphically with points, 1, 1. If you shifted up, which we did in red, it now becomes 1, 1 plus 2. So 1, 3. And the shift down went to 1, became 1, 1 minus 1. which is 1 comma 0. Let's digest that before we move on, since that's a lot of writing and not a lot of talking. So we've been doing a lot of drawing, so let's reiterate what's happened. We've added a 2 on the outside with the shift up. And what that's going to do is going to keep all the x coordinates the same, but the y values, the function values, now have an additional 2 units to add on top of them. Or 1 unit less with the shift down. So the x coordinate is still the same, but the y coordinate gets 2 added. The x coordinate stays the same, but the y coordinate gets 1 minus from it with the blue. That's what a vertical shift is. And that's a linear transformation. It's just moving it up or moving it down. Nothing else changes. Any questions on those?
How come the red one? What's another? Just that one big.
Cause your B is essentially your Y, right?
Say again?
Your B is essentially your Y, right?
What do you mean by B? And sorry, Thomas, I will get to your questions.
When we're doing the Y equals MX plus B, of course, we don't have an M right there. But when we're trying to get the B,
Oh, so the the B is usually reserved just for lines, but yeah, like the X the Y intercepts, yeah, it just gets shifted up to whatever number you've added to it or subtracted, or shifted down to whatever number you're subtracted, or up to whatever number you've added. Is that okay?
yeah,
And so, Thomas, what was your question again?
Okay, so why is the red line a lot higher than the other? Usually the other two, because it goes up too, but
Mm-hmm.
isn't that already black in the blue line? Because it always goes down too, because there's like one.
So every point gets shifted up 2 units. So I mean, I'm not perfect at drawing. And that's why this kind of looks a little wonky. But if I shift this up 2 units, it matches almost perfectly.
But if you go down, it should.
It shifts down and it's almost perfect. I'm actually pretty impressed with how my ability.
pretty good.
Thank you. I heard the crumbling of a water ball and I thought that was clapping, so I'm pretty bummed out. Say again?
Yeah, it shifts down. Oh, because that shifts up, down there. Okay.
Good?
Yeah, I got it.
All right.
Because I was treating like each number line was 2 like orbits, actually 1, 2.
Yes. So just so we're clear, there's these tiny little tick marks. I'll when I redo the notes, I'll like make some edits. I'll make those things a little bit thicker so it's easier to see. Sorry about that.
Because I thought it says 2, 4, but it's 1, 2, 3.
Yes. Okay. Then we have the horizontals. Let H be some positive number. Once again, it could be 5, could be 10, could be 3 billion, could be square root pi. Who knows? Then y equals f of, let me make sure f of x minus h is a horizontal shift right by k units. And so x naught y naught goes to x naught plus h comma y naught. That looks weird. I will tell you, and this is a thing that you just need to kind of a mantra you need to accept. The horizontal stuff is the opposite of what you'd think it would be. It's like horizontal stuff, opposite. Vertical stuff, very nice. So notice that it's x minus h, and now it's x naught plus h. And we'll explain that in just a moment. So those are the shift rights. And notice that the minus sign, the minus h, is on the inside of the function. It's on the inside of the parentheses. It's not on the outside. Horizontal stuff will happen on the inside. Vertical stuff will happen on the outside. So if you have y equals f of x plus h, that is a horizontal shift left by h units. So instead of x naught y naught, we now have x naught minus h, comma y naught. So in the context of this picture, we have the our original graph is kind of grayed out, is a little bit grayed to see what's happening with the red and the blue lines. So you see that it's just shifted left or right. So this value right here is x naught plus h, and this is x naught minus h. And we'll actually, if we have time, we'll mess around with Desmos to see some cool, some visualizations of these things. So, in a graph format, let's look at a specific example to visualize this. So the parent function this time, I'm just choosing the parent function, right? I like this is just an example. It doesn't have to be. I could have just as easily used absolute value of x or 1/x or something like that. But I chose to do it just for giggles. I don't know. Another version could be y equals x. A shift left would be x plus 2 cubed. And we'll graph that in blue. And then a shift right would be something like y equals x minus 1 cubed. We'll graph that one in red. And I totally understand if you're wondering why. We're going to explain it. If you look at the bottom of the page, it says, why does that counterintuitively? And we'll explain it there. But so if it's adding something, notice that the plus 2 is on the inside of the parentheses now. Like if I did f of x plus 2, it would be on the inside of the parentheses. It would be minus 1. So this would be a shift left 2. And this would be a shift right 1. So the parent graph, which we're going to draw in black, that has the points. It's an x cubed. That's an odd power of x. So that makes the kind of squiggly line. It always has the points -1, comma 1, -1, sorry, -1, comma -1, 0, comma 0, and 1, comma 1. And it kind of looks like this. So the shift left, you're moving every point 2 units to the left. So this point right here at 1, comma 1 gets shifted 2 units left. 1, 2 to right there at -1, comma 1. 0, 0 gets shifted 2 units to the left to now -2, comma 0. And then -1, comma -1 gets now shifted 2 units to the left to -3, comma -1. But it's the same shape. And a similar fashion for the shift right. Everything is going to get moved 1 unit to the right. So instead of 1, 1, we're going to get 2, 1. Instead of 0, 0, we're going to get 1, 0. And instead of -1, comma -1, we're going to get 0, comma -1. And it's going to look roughly like that. Same shape, just shifted. So what happened in each case? The shift right the point 1, comma 1 went to 1 plus 1, comma 1. So that'd be 2, comma 1. Whereas the shift left 2 changed the x coordinate to 1 minus 2, comma 1, which was -1, comma 1. All right. Any questions so far? Like, if you have a question on why does it happen that way, that one will get answered hopefully with this question at the bottom. Because so it's minus that makes it shift right. So going towards positive numbers, but it's adding on the inside to shift it left. Why is that the case? Why does it behave counterintuitively?
Because of the odd exponent?
It's not because of the odd exponent. It's because of whether it's plus or minus. And so why does it happen that way? It's best to see horizontal shifts as what they do to the origin, where our y value is 0. So almost every single one of the parent functions, save for the 1 over x and the 1 over x to the n and 1 over the x to the m, all of them end up having the origin as a point on them. Did you notice that? Maybe you did, maybe you didn't. X has the origin point, y equals x has the origin point, f of x equals the absolute value. It had the origin, had 0, 0. X to the second power, or even powers of x, they had 0, 0. Odd powers also had 0, 0. Square roots also had 0, 0. Odd roots also had 0, 0. Every single one of them had an origin. So what do I mean by this? What do I mean by best to see them as what they do to the origin? For y equals x minus 2 squared, we would need to add 2 units to the x value to get back to a y value of 0. So write that down and then we'll explain what we're trying to say. For y equals x minus 2 quantity squared, in order to get back to a y value of 0, we need to plug in 2, right? That's the only way it would be 0. We plug in 3, it becomes 1 squared, which is 1. We plug in -2 or -1, it becomes a negative number squared. But in order to get 0, we have to be at 2, right? So the original function was here, but now it has to get shifted. Oh, I did -2. Oh, like I did +2 in this case, but I'll do. Darn it. I'll need to change this in a little bit. Doesn't matter. So in order to get this function to be back at 0, I'd have to put a y value at 2. Oh, this is terrible. I'm sorry. Change that up. Okay, let's restart. So I can explain it again. So for x, this is a completely different function. This is not one of the ones we graphed up there. This is y equals x minus 2. We would need to go 2 units to the right to get back to 0. So even though it's minus on the inside, you have to basically counteract the fact that you subtracted 2 to get you back to where you started. So you have to move yourself 2 more units positively, which is in the right direction. Whereas if it's x plus 2, in order to get back to 0, you have to plug in -2. So you have to move to the left on the number line. Even though you added 2 on the inside, to counterbalance the fact that you need to be 0, you'd have to plug in -2. So you have to move 2 units to the left. That's kind of the intuition behind it, is you have to kind of counterbalance what you've done. Yes.
Apply for horizontal.
Because in essence, it has to do with when you're applying the number. So here we're applying the adding or subtracting before we compute the function. So in the first example with vertical shifts, we compute what f of x is, then add k. We compute f of x and then subtract k. It happens after the fact. Whereas here, it happens before. We take in an x value, then we like before we even compute what the y value is, we subtract h or we add h. Does that make sense? That's the reason why it's different. It happens on the inside before we actually compute anything. That's the main difference. And because we're computing it before we actually compute the function value, we have to kind of counterbalance what we just did. Yes.
Is there a possibility to write what you just said about the counter this
Yes.
expression? Because I know, I see that you have it as like y equals parentheses x minus 2, but like I'm assuming we're gonna substitute y for 0. And essentially, whatever number we have next to x, we're trying to make sure that it can go back and forth. Essentially, that's what I'm getting, right? Just from your words.
Like, yeah, we're trying to get back to 0. So if it was subtracting 2, in order to get back to 0, we'd have to plug in 2. If it was minus 3, we'd have to move 3 units to the right to get back to 0, because that would make it 3 minus 3, which would be 0. If it was adding 4, we'd have to plug in -4 to get us back to 0. It's weird. And that's kind of one of the things that's hard to accept in this situation is it happens essentially because it does. It's counterintuitive to what you'd like. And like that's honestly, in my opinion, that's kind of the saving grace of it is if you remember that it like horizontal stuff acts counterintuitive to what you think, then that like as long as you memorize that concept, it will kind of fall into place. We will do plenty of examples, by the way. So this isn't just the only example before we move on. Once we've gotten through all the different types of linear transformations, we'll do some more examples. All right, let's take our next break. Let's come back at 11:43 or at 11:44. Let's do 11:44. People watching the recording do 10 squats. I don't care. Math. All right. We had a yay when we got back, so that means we're gonna have a good time. All right. Good news is then we got vertical stretches and compressions. The book will call it just vertical stretches, but I want to call them compressions as well. And there's good reason for that in my mnemonic device later on. So let A be some positive number. Could be 5, could be 2,000, who knows. Then if A is greater than 1, then y equals A times f of x is a vertical stretch by a factor of A. So instead of being x naught, y naught, it now becomes x naught, comma, A times y naught. Instead of x naught, y naught is now x naught, comma, y, A times y naught. So we multiply the y coordinate by A. And this gets back to Ben's question. With vertical stuff, it's happening after you've plugged in the function value. So now it's just affecting the y value. So it's a vertical stretch by a factor of A. If A is greater than 1, and we'll see an example of it soon enough. And if A is between 0 and 1, so A is sandwiched between 0 and 1 like that, then y equals A times f of x is a vertical compression by a factor of A. Now here's the weird thing. This one also goes to x naught, comma, A times y naught. But I've deliberately color-coded it to show that it's different only because now the A value is between 0 and 1. It still does the same thing because at the end of the day, we're taking a function value in f of x and we're multiplying it by a value. It's just, it depends on what the value is. If the value is larger than 1, like maybe 2 or 3, we're doubling or tripling it respectively. But if it's between 0 and 1, like 1/2 or 1/3, we're halving it or we're thirding it or something like that. So here, what happens is imagine you've got some silly putty and you kind of like squish the picture, right? Did you guys ever do that with silly putty? Like put it on a piece of paper and you get a bunch of like words on it and then you like stretch it vertically or whatever. That's essentially what you're doing. So here in this picture, when A is greater than 1, all the Y values get like doubled or tripled. In fact, what I did here is I actually did 2 times. These are arbitrary graphs, but what I did is I doubled the values. So here's the original Y naught value, and then I doubled it to get up here. So this is A times Y naught with A greater than 1. And here is A Y naught with A between 0 and 1. Hey, yo.
You're gonna be allowed to use decimals on the.
I wish. I wish.
We gotta memorize all the, yeah.
Yes, but the intuition, it really helps. As long as you understand what function notation is. Did you have a question? Oh, yes, of course. So all it does is it doubles or halves the y coordinate. That's what a vertical thing is. Notice again, it's on the outside of the function. It's on the outside. So as an example of this, so once again, our parent function, I'm going to draw in black. It's the absolute value function. A vertical stretch, let's look at something like y equals 3 times the absolute value of x. We'll draw that one in red. And then we'll do a vertical compression. We'll do something like y equals 1/2 absolute value of x. So it's happening on the outside of the function. So the original function, the absolute value function, it makes the V shape and has the points -1, 1, 0, 0, and 1, 1. And it makes that V shape. Like that. And so, unlike with shifting, where it's a specific number each time, it's now a tripling process. So the vertical stretch is a stretch by a factor of 3. And the 1/2 is a compression factor of 3. The textbook, and Alex will probably say it's a shrink, but please remember that shrink and compression kind of mean the same thing. I'm calling it a compression, and there's a good reason why in a second. For a good way to memorize this stuff. So a compression factor of 3. Or, sorry, not compression factor of 1/2, not 3. What am I doing? So what's going to happen is every coordinate is going, for the red, for the stretch, every coordinate, its y value is going to get tripled. So for this point right here, -1, 1, +1, its y value 1 is going to get tripled to 3. It didn't go up 2 units, it got tripled in value. So at 1, 3. Right there. If I were to look at the point -2, 2 right here, tripling its y value would make it up to 6, because 2 times 3 is 6. So it triples whatever value. 0, 0. If I triple its y value, where is it? 0. Triple of 3 times 0 is 0. So it stays here. And then 1 comma 1, tripling its y value. 3 times 1 is 3, so it goes up to here. And so it ends up looking like this, just a much more steep version of what we had. Whereas the other option, if you compress it by a factor of 1/2, then it means that everything is going to get half of it, every y value is going to be half of its size. So instead of being -1 comma +1, it's now -1 comma 1/2. I went half the size. If you're looking at the point -2 comma 2, half of that size would be -2 comma 1, because taking half of the y value 2 makes it 1. But we can just stick with that point there. Then half of the y value 0 would be 0. So it still sticks around. And then similarly on the other side, it becomes 1/2. Oh, wait. Let me make that. There we go. Like that. So it's like you took the silly putty and you kind of squished it together for this one. Or you took, when you have the box, if you put an image in Word, like this, like here's the image. When you put it in, and then you bring it up or down, like you work with the vertical bar here, it goes up or down, and it kind of squishes whatever you have, right? Or a case in point, let's take this picture here. If I take this picture and oh no, it won't let me do that. Darn it. Never mind. I can't do everything fun. Okay. So it vertically stretches the thing. It pulls it out. So what happened to 1 comma 1? Well, with the stretch, the x coordinate stays the same. Vertical stuff only affects the y coordinate. Horizontal stuff will only affect the x coordinate. That's key. So the x coordinate stays the same, and then we tripled the y coordinate. 3 times 1, which ends up being 1 comma 3. For the compression or the shrink, as the book will say, we keep the same x coordinate, but now the y coordinate is 1/2 of what it was. 1/2 times 1. So it becomes 1 comma 1/2. On Alex, if it has a compression, sometimes you won't get nice numbers. You'll need to use the plotting point feature. So make sure you feel comfortable with that button. Like click on the little, it should be like a little XY grid and a little X on it. I think the icon looks like this. And then it has a little X here. Use that feature and that'll allow you to plot a point. So if it won't, usually it's pretty good at making like a graphing grid with half tick marks mentioned everywhere. So you can plot a halfway point, but usually it doesn't do it for like thirds or things like that. So in that case, you're going to need to use the plotting point feature. Okay. Then horizontal stretches and compressions. I've got good news, but we'll talk about it in a second. So let b be greater than 0, be some positive constant. Then if b is between 0 and 1, then y equals f of b times x is a horizontal stretch by a factor of 1 over b, which we'll explain in just a moment. Why it says a stretch of 1 over b is that if b is 1/2, then it fits into this criteria. It's a number between 0 and 1. And saying a stretch by a factor of 1/2 makes no sense. How does it stretch if you're using 1/2? But if you say 1 over 1/2, that results in a stretch of 2. So that's why it makes sense. Why it has to be that way. If b is greater than 1, then y equals f of b times x. Same thing. It's the same thing. It's just with a different context on b, is a horizontal compression. The good news is, oh yes, Ben.
Be greater than zero. What happens if it's negative?
If it's negative, so we're going to ignore that case because that has to do with the next type of transformation. So we'll treat that as a separate entity as well. But great question. We're going to assume that B is always positive here because otherwise then you're combining two different transformations at the same time. Great question. Now the good news is I will never test you on this, and I'm pretty sure I've vetted all the problems on Alex so that they don't have horizontal stuff happening. Because, in my opinion, horizontal compressions and stretches are not useful because every horizontal stretch and compression can be converted into a vertical stretch or compression, and with a little bit of algebra. So, for example, if you have y equals the quantity 3x squared, that is a compression. That is a horizontal compression by 1/3. The B value is larger than 1. And so back to the point, the reason why it is bonkers is the way it works is differently because it's affecting the X value before you're able to even plug it into the function. So the reason why if B is greater than 1, you have to counterbalance the fact that you did that. That's what's happening essentially. But instead of writing it this way, we could simplify it to y equals 9x squared. And now this is on the outside. This is a vertical stretch by 9. So every horizontal compression or stretch can be converted into a vertical stretch or compression. So there is no need to study horizontal compressions or stretches. There's like a handful of cases where it might be helpful, but in those cases, if they showed up in your daily life, you'd be surprised. And one thing people have asked me in this course, when is this useful? And the answer is nowhere. I have looked tirelessly for an example of like how to say like, oh, this is really, really important. And I can't find one. It's merely a fun practice on how to manipulate a function and how it works. It does have future mathematical implications, mainly the shifts. The shifts are probably the most important ones. They actually do have some useful applications in later math courses. The vertical stretches and compressions also somewhat useful, but horizontal stretches and compressions not useful at all.
It's only useful to nerds.
Yes, only useful to math people. The last type of transformation are reflections. So, and which one did I want to do first? Yes. So, because otherwise it becomes really, really hard. For this one, it needed to be in two different pictures. But if you have y equals negative f of x, so negative the quantity f of x, the minus sign is on the outside. That represents a reflection across the x-axis. These ones always throw me off unless you learn the pro tip at the bottom, which we'll talk about in just a moment. So the x-coordinate stays the same, but the y-coordinate now becomes negative. And if you think about what the function notation is, it makes sense. We're computing what f of x is, and then that's the function value, the y naught, and then we're tacking on a negative sign after the fact. So the x-coordinate got plugged in, it got taken care of, and then we applied the negative sign to the y value. That's why it's now x naught, y naught. So you can see it on the picture. Up here, this is an x-axis reflection. You see that the x values stay the same, but the y values get flopped. This positive y value is now negative. This negative y value down here is now positive, and so on and so forth. It reflects everything at all the y values. Then if you have the the negative sign on the inside, if you have y equals f of the quantity negative x, notice the difference. The negative sign is on the inside. This is a reflection across the y-axis. So notice that all the points, the x values stay the same. Sorry, that's not true. So this one becomes negative x naught. Comma y naught. Notice that if you're looking at the grand scheme of things with the secondary option, with the reflection across the y-axis, nothing happens to the y values. There's no there's nothing on the outside. Whatever you plug in will just give you a function value. So nothing really happens to the y values. It's that the x values get swapped. So here's the original point right here, x naught, y naught. Now it gets flipped over to here. This point here gets flipped over to here. This point here gets flipped over to here, and so on and so forth. Sorry, I should have said it the other way. This point gets flipped. This point gets flipped. This point gets flipped.
Y-axis reflection.
Yep. It's like you took the function and you rotated on that axis, the y-axis. So I might even be able to write like this. You flip-flopped it on the thing, and this one you flip-flopped it here. So as an example of each of these, let's look at the parent function f of x equals the square root of x. And then we're going to reflect across the x-axis. That'll be y equals negative square root x. And then reflect across the y-axis would be y equals the square root of negative x. So, excellent point. I thought we couldn't have negatives on the inside of the x inside of the radical. X is a variable. So if x is negative, it's a double negative and it works out. So if I plug in -5 into this, then it works. Because it'll be -5, and that's the square root of +5. So it's okay. So we can do that. I'm glad someone mentioned that though. It does look weird at first, but because x is a variable, it is okay for that to happen. So the original function has the point 0, 0, 1, 1, and it also has 4, 2, but we can't really, my graph doesn't go out that far. And it looks roughly like that. The reflect across the x-axis, all the points just become negative versions of themselves. All the y values can become negative versions of themselves because the minus sign is only affecting the y value. It's on the outside. So 0, 0 gets reflected across the x-axis, but it's on the x-axis. So as we say in Magic the Gathering, it fizzles. It doesn't happen. Not that I've ever played Magic the Gathering, but if I did, that's what we would call that. This point, though, so this point sticks around. But this point gets reflected down here to 1, -1. And then so on and so forth. It gets a reflected version of itself. And then the same thing is true for the y-axis reflection, well, but in the opposite perspective. This point gets reflected across the y-axis, but it is already on the y-axis, so it fizzles. It doesn't happen. But this point gets reflected to over here at -1, +1. And then we're all good to kind of model it. It doesn't need to be perfect, but there it is. So what happened to 1, 1? With the reflection across the x-axis, the x-coordinate stays the same, but the y-coordinate changes. With
If it's a double negative, like a negative outside and a negative inside, you would have it on quadrant 4?
Mm-hmm. Exactly right. I mean, it might depend. There's a couple situations where things kind of cancel each other out. But yes, here, it would get, if you had negative square root of negative x, it would then be down here. And that brings up a good point. So multiple transformations can happen to a function, and they have a certain order. Here, if we had negative square root of negative x, it would first get reflected, then it would be reflected that way. And it would be, as Hector suggested, it would be down in quadrant 3, actually. The bottom left, the third quadrant. But yes, so you can have multiple reflections. Well, at most 2, but
That square root is really throwing me off because the point that we've graphed for the x reflection, that just becomes y equals square root of negative x, right? Because it's just the -1 in there now.
yes.
So how come that is implying now that it's a real number when usually we don't get real numbers inside of it?
So because now for the blue curve, that's the reflection across the y-axis. Now its x values are always negative. So when we plug in a -1, it becomes -1, which becomes +1.
Yeah, but I'm talking about the reflection on the x-axis.
So that is on the outside. So all the x values are still positive. So
I understand, okay.
yep. So it doesn't affect the x values, it affects the y values now. So that brings up my pro tip. This is sorry, I forgot to write the last point, which is that the x value gets flipped. Y value stays the same. So the good mantra to have for this section, if you can memorize this, then everything kind of comes into play. Vertical stuff. So vertical shifts or compressions, vertical shifts or vertical stretches or compressions, they always happen on the outside of the function. They're not inside parentheses, they're not inside radicals or anything like that. They always happen on the outside. And they only affect the y coordinates. If we go back through the vertical stretch, it only affects the y coordinate. The vertical shift, it only affected the y coordinates. The outside reflection only affected the y coordinate, the outside, the vertical stuff. Whereas the horizontal stuff happens on the inside and it only affects the x coordinates. The thing on the inside, it affected the x coordinate. The thing was on the inside, we didn't write it down, but because we don't need to do it, but it'll affect the x coordinate. Horizontal shift happened on the inside, only affected the x coordinate. So if you can remember that, and then remember that horizontal stuff is always the opposite of what you'd think it would be, then everything kind of falls into place. That is a very, very useful pro tip.
The horizontal. The opposite.
Yes, horizontal stuff is opposite what you'd think. Come on, I want a box, not an oval. There we go. All right. Vertical stuff happens on the outside. Horizontal stuff happens on the inside. And they affect the y coordinates and the x coordinates respectively. Only. They don't do anything with the other coordinate. So when it comes to graphing these things, step 1 is so in these types of problems, we're going to tell you the transformations that need to be done. So, I'm going to say it first needs to get shifted, then it needs to get stretched, and then it needs to get reflected or something along those lines. So the thing you want to do is create your functions equation by following the steps, following each transformation. Step 2 will be to draw a small parent function for reference. You don't necessarily have to. Step 2 is kind of optional. If you have them memorized in your head, then you're awesome. You get kudos. You get brownie points for having those things memorized. Coolio. But I need to draw them to see them. And then on the actual graph itself, using your mini graph of your parent function, use your pencil to carry out the transformations in the order given on each important point of your parent graph. upon performing the last transformation, jot down your location. I don't recommend plotting the points until you've got them all down. You'll see why in just a moment. So don't plot them until you've finished all the transformations of all your important points. Otherwise, it starts to get way too busy on the graph and gets confusing, in my opinion. And then step 4 is to plot those points and construct your graph. So I'm gonna go ahead and I'm gonna claim it now. Looking at timing, I don't think we're going. I think we're going to basically just finish 1.7 on Thursday, which means that we won't really get enough time. Like we won't really get enough time to digest it before our exam. Our exam is next Tuesday, technically speaking, but I'm actually going to shift it to next Thursday. So I'll send out an email reminding us of that fact. Let me. So let me just change exam date. So I'm gonna go ahead and just claim it right now. I'll send out an email, but I'm changing the date of exam 1 to Thursday of next week, not Tuesday. So that'll give us a little extra time. If that screws up your schedule in some way, just let me know. Like if you were planning, like if you have an exam that day as well, we can work around that. But I'm hoping. I mean, I'm hoping most people are excited to have an extra day, extra 2 days to study. But if not, if that really screws up your schedule, just talk to me. I'm happy to work around with it. Yes.
Did you already put in the reading grades for?
No, I haven't graded them yet. I'll be grading them soon. I've got another exam from another class that needs to get finished. But first for their redos. Yes.
What's that say?
Construct.
Construct?
Doesn't actually look like construct. Let's change that U, make it look better, and look at that an actual R.
Thank you.
Yes. So I'm just going to claim that for now. We're going to change the date of the exam till next Thursday, but I'll send out an email to remind us of that fact for people who aren't here as well. There.
What camps is it gonna be on?
It's going to be on all of Unit 1 that we've gone over. So there is another unit in Unit 1 called 1.8, which is combinations of functions and composite functions, but that will be normally I teach it then in regular 126, but based on how 126E is comprised, it's better to wait on that material. So that one's going to be later. So, but it's just going to be 1.1 to 1.7. So back to the problem at hand. Find the equation of the function that is graphed by following the transformations on the graph of f(x) equals x squared. Then graph that transformation. So the parent function given is y equals x squared. That is an even power of x that makes the U shape. That's Soldier Boy's favorite one. Once again, the U. And so that has the points 0, 0, 1, 1, and 0, -1. That's what this looks like. It also has the points 2, 4, and -2, 4, but 3 will suffice for me. That is y equals x. That is f of x equals x squared. So I'm going to color code these. This is the first one. We're shifting up 2 units. Why won't it let me highlight it? Fine, I'll do it this way. And then we'll do purple for the set. Not purple, let's use orange. So, first things first is a shift up 2 units. So we start with x squared. The first shift is a vertical shift. We're going up. Vertical stuff happens on the outside and it behaves very nicely. So if we're going up 2, we're going to add 2. So it's going to be x squared plus 2 on the outside. Then we do the next shift. We're going to shift. So any questions on that? It's a vertical shift So that means it happens on the outside. That's why it's x squared plus 2 on the outside. And it's vertical. Vertical stuff behaves exactly as you'd think it would. Horizontal, this one, next one, shift right. That is moving left or right. That is horizontal. And horizontal stuff happens on the inside of the function, and it's counterintuitive to what you'd think. So instead of it being x plus 1, it'll be x minus 1 on the inside. So it'll be x minus 1 quantity squared plus 2. That is our new function. That is the transformed function. The first thing made it add 2 on the outside because it was a vertical shift. The second thing subtracted 1 because it was a horizontal shift. It happens on the inside of the squaring. And that gives us our answer. So now that we have our parent graph, now if you have this in your head, awesome. And you can just memorize these 3 points, that's great. Otherwise, if this problem shows up on the exam, I will provide a little small graph for you to draw your parent function. And that will be worth partial credit if it shows up. So let's take each point. Let's start with negative 1, 1. It gets shifted up 2 units. 1, 2. And gets shifted right 1 unit to right there at 0, 3. Then 0, 0. Shifted 2 units up. Now we're at 0, 2. Shifted 1 unit to the right. Now we're at 1, 2. One, 1. Shifted 2 units up. 1 unit to the right. That's 2, 3. And those are our 3 points. I want to show you why I don't plot them. So once again, so 0, 3. Then if I have, well, in this case, it's not going to be too terrible, but it just starts to muddy the graph. I like to plot the points on the side and then plot them. But if you feel comfortable plotting them and then moving on, that's fine too. I just find that it starts to muddy up my graph. So I'm going to plot those 3 points, 1, 2, and 2, 3 right there. And then I will connect them with a U-shaped graph. Like that. Because it should look somewhat similar. It should look like the exact same graph, just shifted around.
Are you gonna put the parent on there?
No, just like otherwise the graph would get way too busy.
Okay.
So I use this for reference only. But you can draw both of them on there. It's not wrong to do so. But if this is on an exam, please highlight which one is the correct one. So anyways, that's all the time we have for today. Alita, you have a question?
No.
Oh, your iPad, gotcha. All right, guys. If you have any questions, feel free to email me. Otherwise, you guys have a great rest of your day. I'll see you on Thursday. One more time, just to say it out loud again, the exam is going to be shifted until next Thursday. There will be a review posted pretty soon, but I'll get to that then. All right. See you guys then.